a first principles approach to life sciences. This is the big opportunity that we see that CRISPR and other technologies enable. I attended a seminar today organized by Syntego and other companies about the state of the biotech industry, in particular the CRISPR-driven biotech industry. I'm going to elaborate what the difference is and also what the big takeaways are on the first day. I think it's worth having this discussion already, even though there's another day tomorrow, because I think the most interesting aspects are, number one, that we have a first principles approach, that we start from sort of some ground truth or something that is given, like a DNA or something along those lines, and then we build up from that. And I think Daphne Koller, one of the attendants, said it very well. She said that the taxonomy of diseases today is very wrong because it's kind of starts at a much higher abstraction level, at a level where we just see, let's say, oh, you have a problem with eyes, that's an eye disease, and you have a problem with liver, that's a liver disease, when in reality, maybe the disease is the same disease, which is, it might be a certain monogenetic problem that causes both diseases to be the same. So maybe we should, instead of calling it the eye disease or the liver disease, we should call it, this is the monogenetic A1 disease or something like that, because it has the same underlying problem and can be fixed with the same underlying technology, and that's where CRISPR comes in. So this would be the first thing. And the second thing is that we have already a conversation of how AI can influence drug discovery and generally research. I think it ties to the first aspect, and that is that we have a much more data-driven approach also to medicine and life sciences, again, driven by the fact that we can start with something like a DNA and then build up from there RNA, protein. We have AlphaFold also help us to predict protein folding and therefore the function of protein. So we have a lot more, let's say, downstream first principle type reasoning, or the ability to reason. And I want to use the computer architecture model to elaborate on that, which is that we have all these layers. It starts with the transistors and then goes all the way up to the algorithms. And the problem in biology is, of course, we don't have the transistor level in biology because that's what nature did. It's not us who have developed that. It was nature. So what we have is very high abstraction levels, things like we call medicine and pharmaceuticals and things like that, which is a very high abstraction level. And we can't get down to the bottom of it because we don't know. And with CRISPR and genomics and synthetic biology, we have a better chance to get lower into the layers of the abstraction level of nature, and that hopefully will help us understand life sciences much better. This is the Not Even Wrong podcast. It's September 21st, 2022. This is Krim Delco. For the day, the fund is down 2.3%. The market's down 1.9%. For the year, we're down 26.2%. The market is down 20.9%. We're outperforming by 5.2%. So the Fed decision was today, and they raised rates by 75 basis points. But there's another thing which they said, which I think spooked the market a bit, and that is that they're going to do anything necessary to bring down demand. Basically, the Fed reiterated the desire to push and push until the inflation abates. There's not even a conversation about this anymore, and I think this is the main message of today. Nothing surprising, to be honest, but I guess the markets just really understand that the Fed is committed, and we'll see how far that goes and how much carnage the Fed is willing to accept on that journey to lower inflation. They want the housing market to stop growing. They want things to calm down. They want inflation to stop. This is absolutely clear. And for us, it's, of course, painful like for everybody else. But the thing, I think the most important thing here is that we have an asset, which is Tesla and CRISPR, so assets that will grow and create wealth no matter what. In the meantime, we have to survive with leverage. This has been the narrative of this year for us. It is still the narrative of this year. The only thing that matters in volatility type situations is your leverage. Volatility is a feature, not a bug. It's part of wealth creation, and there's nothing wrong with it. And we can't avoid it, or we shouldn't even try to avoid it. What we can do, though, is focus on what will be long-term value creation, and that is the only thing that matters. Now, having said that, let's talk about long-term value creation. CRISPR and genomics and the life sciences based on CRISPR and CRISPR technology for us is one of the biggest trends in the world right now. That's why we're invested about 10% of our capital in that type of business. And I want to talk about why that is and what the big takeaways are, and use today's seminar that I attended It was a seminar called The State of Biotech, organized by Syntego. Shout out to Syntego and other companies, or sponsored by Syntego. It doesn't matter. I'll put it in the show notes. The point is this. When you have a new technology like CRISPR, which allows you to efficiently alter the sequence of DNA and do that at low cost, you enable iteration, you enable try and error, you enable a more industrial, data-driven approach to science. And this is the key. This is what it's all about, as far as we're concerned, that we want to see more, less of a, how should I say, bespoke approach and more of an industrial approach. What does that mean? And I want to use the computer architecture model as a proxy here. So in computer architecture, we have different layers of abstraction. So we start at the bottom with the actual transistors, which are the bottom of the abstraction level. Then we create gates. Then we have logic based on gates, and then we go up to the instruction set architecture, which is the contract between the software developer and the hardware developer. Basically, the hardware developer tells the software developer, "This is what you can do. You can, let's say, access memory in 3-bit sequences, and the memory is byte addressable. So each 3-bit address has 1 byte of memory space, or it has 2 bytes, or 3 bytes, or 4 bytes. This is how many times memory refreshes. This is what kind of instructions you can access in the arithmetic logic unit. So you can have an adder or a subtractor or a shifter, things like that along those lines. That's the ISA. So you keep going up the abstraction level. And in biology, it's very similar. If you want to look at the world as a compute problem, you can say, okay, even let's say a cell or a human organism, all of these things, they're all abstraction level. So the human is an abstraction level, and then the cell is an abstraction level, and the DNA is an abstraction level, and so on and so forth. And as further down you go, the more first principle approaches you can use. In other words, you can start from there and then build up and say, okay, and this is what I mentioned in the prelude. Daphne Koller said, let's say even our disease taxonomy shows how bad it is right now in medicine, because we call diseases based on how they seem to us from the outside. Let's say we have an eye disease, we have a liver disease, we have liver cancer, and those things, which really we know that that's not the truth. The truth is that those diseases are caused by certain underlying malfunctions, so malfunctions at lower levels of the abstraction level layer. And if we could understand what they are, then we could also fix them at the much lower level of abstraction, which then means we could have much better cures. This is the idea of CRISPR-based technology. This is what Jennifer Doudna, for example, is propagating. Also, she's talking also about agriculture. So if you want to have drought-resistant rice, right? Drought-resistant rice. Drought resistance is a higher abstraction level. It's an abstraction level at the human interface between us and nature. We know that, lack of water makes, let's say, rice not grow. So how can we change that? If we understood what the underlying causes are for water necessity and water absorption, and then work with that, and then maybe change the genome of the rice in a way that it absorbs much more water much faster, the same way, let's say, plants in the Atacama Desert can survive, or in any other desert, then we could maybe have more rice on Earth and therefore feed the world at much lower cost. So this is another example of first principle approach to life sciences, which is really what we're trying to achieve at Orange Capital Partners. This is why we're invested. We are all about the Popperian approach towards life, which is try and error, iteration, lower cost of error correction, and CRISPR technology allows that for life sciences. That's why it's such a big opportunity. Before I go to further elaborate on all the opportunities, I just want to mention quickly also the downside, which is what we see, unfortunately, is a bit of a lack of entrepreneurship. So we see a lot of people excited. Jennifer Doudna is a good example. Church is another one, and Liu, and all these people. But the problem with biotech is always the same. These professors, they just spin up companies, but they're not committed to really solve the problem at scale. Nobody is scaling up to become the Elon Musk of life sciences. This is the problem, unfortunately. And we at Orange Capital Partners are trying to help solve that problem by finding those people, investing in those people. This is part of our mission. to generate wealth by investing in fundamentally new concepts and engineering practices with large impact. We're trying to have a large impact by finding those people that can take all those concepts and actually turn them into tangible businesses. This is the idea. Unfortunately, also, we haven't been able to do much more than find companies that maybe have the potential, but that's obviously a podcast for a whole other, an episode for a whole other podcast. So the first point that I want to make is, again, the abstraction level, thanks to CRISPR technology, can be lowered, very similar to computer science. Once we discovered the transistor, we could go lower in the abstraction level, solve problems down there, create better transistors, and then go from there and then kickstart Moore's law. And hopefully we can have something like that, because we are now lowering the abstraction level. We could have something similar also in biology. This is the hope. We're on track. There's some fantastic results, and I always bring up Intellia, because the problem that Intellia is solving is not just that it's solving a certain disease problem with CRISPR technology, but it's also solving the delivery. It's doing in vivo delivery, and Doudna today talked about this. The in vivo delivery problem is serious because ex vivo delivery is very expensive, and we have some in vivo approaches with viruses and so on and so forth, but that's way too risky right now. We're not sure if it works, and the safety issues are problematic. So what Intellia is doing with lipid nanoparticles and mRNA technology is very promising, and hopefully we will get to a point where delivery technologies actually will improve to the extent that we can talk about injections versus ex vivo treatment of problems. Before I go to the AI side of things, maybe as a bridge, I just want to use one of the most promising companies that we own is Caribou, because Caribou is working on, in my view, the most exciting problem in life sciences today, and that is allogeneic CAR T cell therapies. What is that in a nutshell? It's off-the-shelf T cells that can be harvested from anybody, re-engineered and injected in people with cancer to fight their cancer. That is the holy grail of cancer technology. Again, it's absolutely mind-boggling if that works, because I think this would be the penicillin of cancer, lowering the cost by orders of magnitude, and also increasing the efficacy, which for many patients sometimes it's more important. So the second point that was discussed today was applications of AI in life sciences through CRISPR technology, and I think it's tied to the first aspect, which is this idea that we're going lower in the abstraction level. The same way that machine learning and AI have been successful is because we've been able to go lower in the abstraction and then rebuild our software development platforms based on software 2.0, based on algorithms and data-driven models. But we had to go lower in the abstraction level to get there. And I think that's why the hope is here. Like, for example, we can have better data collection, more relevant data also for machine learning to solve problems in biology. Now, before, one thing that we discussed also yesterday at the NVIDIA conference was discussed between Jeff Hinton and Joshua Bengio and Jan LeCun, was this idea that we have a better representation of the world, of complex worlds, with neural nets, so deep neural nets and gradient learning. So this is a better way to represent complex systems. So biology is one of them. So it's a natural application. And AlphaFold has already been shown to be a very good candidate for biology problems. And why should we stop there? I mean, there's a lot more fruit to collect here, even low-hanging fruit, before we go to the higher-hanging fruit. And I think in this realm, I also actually wanted to ask a question to the panel, which was what models are most suitable for life sciences? Are we talking about supervised learning, unsupervised learning? Is it reinforcement learning? Or what kind of, should we represent the world more as this is the right way and please learn? Or should we represent the world more as a game? So a little bit like AlphaFold, where it's a game and interaction between agents and so on and so forth. That is an open question. Unfortunately, I wasn't able to answer the panel. I didn't get an answer yet. Hopefully, I will get an answer at some point. And it was an online webinar, and it wasn't very well organized, so it wasn't exactly very interactive. Let's leave it at that. But still, nevertheless, very useful. And again, the main point that I want to make here, really the most important point that I want to drive home here, is the following: that because we are going lower in the abstraction level of biology, thanks to CRISPR technology, we have the chance to also be having a more data-driven model, and data-driven models, excuse me, can have very, very good success, at least in the beginning. Of course, we will hit some roadblocks, and then we have to come up with better models. But for now, I think it's fair to assume that those models, that data-driven models, could lead to much better results in the spirit of representing biology with deep neural nets and gradient learning. This would be a very good approach. So to summarize, the state of biotech in the CRISPR world is very exciting because it helps us get to lower levels of abstraction in biology, which then allows us to build more bottom-up, first principle type approaches to solutions. And that also brings the second point, which is a more AI-driven solution space for biology, because we believe that representing the world of biology with deep neural nets and gradient learning is a better way than any other way we've had so far, and therefore it's very exciting. Thank you.